Okay, hello everyone. This is the third in a series of lectures about chapter 16. The last thing we talked about was having a wave function to describe a wave in terms of its vertical displacement or its displacement from equilibrium of each element based on the position and the time that has passed. So the question is then, if the speed is a property of the medium, then is there a way to determine that speed if we know properties of the medium? In the same way that when we looked at the simple harmonic oscillator, the simplest, the mass spring system, it turned out that the frequency of oscillations was more or less proportional to the square root of the spring constant K over the mass of the block. So it seemed then that the willingness of the spring block system to oscillate was proportional to the stiffness of the spring. A stiffer spring meant a stiffer spring constant, which created a stronger restoring force and thus leading to faster oscillations about equilibrium. On the other side, though, the angular frequency was inversely proportional to the mass of the block in the system, since after all, the heavier the block, the harder it was to accelerate it with a restoring force. Now, when you have a taut string like the ones that the two Victorian ladies here are holding between two tin cans, or a guitar string, then as you send waves through them, either transverse or longitudinal, every element of that string vibrates. And we saw how in our sinusoidal wave model, all those vibrations of each individual element is actually simple harmonic motion. The idea, though, is that we have each element acting as a simple harmonic oscillator. So it's not just in the mass spring system, we just had this one simple harmonic oscillator, the mass and the spring. But now we're sending a wave through a guitar string, and thus we're causing the whole string to oscillate. So each element is kind of like its own mass block system oscillating up and down. So rather than talking about, how the spring constant or the mass affects the frequency of oscillations or the wave speed, which again, remember that the wave speed actually will determine the frequency of the oscillations, as the wave speed can be written as a product of the frequency of the wave times the wavelength. But rather than talking about the spring constant, since we're no longer using a spring, we're using a string, then it makes more sense to talk about the tension on the string, because in the same way that a tense string basically has a more stronger restoring force than, the stiffer spring has a bigger restoring force than a tenser string also does a better job of moving the particles up and down, oscillating as the wave passes through it, the tenser it is. And the inverse relationship for the speed of waves on strings is that of the speed and the linear mass density. So this is just saying that the denser the string is, then the harder it is for the wave passing through it to accelerate it, to really get the particles moving. So because then the wave, has to kind of do a bit of more work to, and I mean work colloquially, not like work in terms of energy, just that the wave kind of has to um, takes it can't accelerate the elements. It can't accelerate through the elements as easily because the amount of matter in each bit of that medium is dense, while if it's traveling through a less dense medium, then it's easy to pass through. It's easy to move through and displace the particles around their equilibrium position. So rather than talking about k over m, now we're talking about tension over mu. But it's still a similar idea to how stiff something is over how much mass there is. But now that is spread out throughout the whole spring. I mean, sorry, the whole string. Spring, string. Two similar words, if you ask me. So let's put that to the test. We have a wave, and we're doubling the amplitude. We make no changes. What is correct? So if you look through the questions, the speed of the wave, again, that's a property of the medium. So the amplitude talks about the energy of the wave. So it won't be A. Again, the frequency of the wave changes. The frequency is related to the speed. So the frequency will only change if the wavelength changes. There's an inverse proportion. And C says the maximum transverse speed of an element of the medium changes. So the answer here is C. Because if you recall what I said earlier, the elements of the medium, their movement, their position, their speeds, and their acceleration as they're shaken up and down by the wave can be described as simple harmonic motion. And if you recall from the chapter on simple harmonic motion, the speed of an oscillator is proportional to the angular frequency and the amplitude of oscillations. So a taller wave will make the elements of the medium oscillate in this simple harmonic motion, and the speed, now being proportional to the amplitude, will be faster since the amplitude has doubled. Also, just so we remember that although the wave travels through at a constant speed, the elements of the medium oscillating up and down are not with a constant speed, right? Acting as simple harmonic oscillators, they have moments of zero speed when they reach their max amplitude and max speed when they pass through equilibrium, and then there's the in-between. Also, the acceleration is out of phase with their velocity function since their max acceleration is reached when they're at max and minus amplitude. That's when the tension in the string around them is at a max, so they get pulled back down through equilibrium. So quick quiz number 16.4. The idea here is that we send the pulse through and we have a string fixed on one end and another one we can hold by the hand so we can send the pulse through. And this pulse, you're moving it up and down, so we're creating kind of a sine wave of sorts. And on the other end, it's pegged to a wall, and after time t, our pulse reaches it. And the question is, how do we decrease the time interval required for the pulse to reach the wall? So first off, let's look at the first four options. The first four options talk about moving your hand more quickly, but it's still only up and down by the same amount. The other three, V, C, and D, say moving your hand more slowly, moving your hand greater distance up and down in the same amount of time, and D says moving your hand a lesser distance up and down in the same amount of time. So A and B talk about moving your hand and effectively setting the frequency of the waves you're generating. So A will create fast, high frequency waves, but the wave speed will not change because the rope is not changing. Is it rope? Oh, it's a taut string. So if you shake your hand more quickly in A, that increases the frequency of the waves, of the pulses. If you do what B says to move your hand more slowly, you decrease the frequency. But in either case, the speed's the same because to compensate in part A, the wavelength is shorter, and in part B, the wavelength is longer to compensate for the frequency being slower. In C and D, if you're moving your hand a greater distance up and down for C, then you're actually doing more work. You're actually adding more energy to the system, hence a bigger amplitude that's gonna pulse through. And in D, you're lowering the amplitude, so you're decreasing the energy. But energy doesn't determine how fast or how slow doesn't determine how fast or how slow the wave is moving. So the question is then, okay, then what's going to make the wave get there faster? And the equation we just learned talks about the fact that denser strings have slower speeds, and a dense string has a faster speed than one that's more loose. So if you look at the last four options, then the one that makes more sense is to use a lighter string of the same length and possibly same tension, meaning that there's less mass per unit length, which means it's easier to move through the string, I mean. And also we should get a string with increased tension so that we'll move faster through it. So that's our answers, F and H. So the question is though, in the last example, in the last quiz, we talked about effectively sending a wave from a loose end with our hand towards a fixed end, essentially towards some point on the wall where the string just ends. And the question is then, what happens when we reach the string? What happens when we reach the wall? And what will actually happen is that you'll see the wave go to the right and then get reflected back upside down. Because what happens is, as the wave here on top begins to reach the wall, it's gonna try to tug here at the joint. It's gonna try to, like, the wave, the pulse is gonna, coming up here. It's gonna try to like shake and move the point here, the joint, up. But obviously this is well fixed to the wall, so the wall won't budge. And while the pulse is trying to pull this up, then by Newton's third law, it will experience a counterforce from the wall, from the joint, that pulls it down. So the wave, the pulse will get pulled down and come out to the left, completely out of phase. It'll come back upside down. Now, what happens if we don't have like a the one end stuck to a firm wall. What if we actually just have one end that's being held by a loop, by a ring on a pole? So the ring is still keeping tension, so you still have a taut string to send the pulse through, but now this ring is free to move around as the wave receives it. So in this case, actually, once the pulse gets to the end where the ring is, then the pulse will actually displace the ring upwards, and in doing so, then there'll be tension from where the ring is to the rest of the string, and then the restoring force from the tension will bring the loop back down. And in doing so, the loop will start a pulse moving to the left with the same amplitude as before. So again, the pulse reaches the ring, it gets displaced upwards and then pulled back by the tension from the spring. And in that movement, then it creates a counterpulse moving back the other way in the same position, no inversion. So this is what's called sometimes the free boundary condition. And here's an example. We can show the two cases. I wish we could make it full screen, but so the top one is we have like a hard end, and the bottom one is the loose ring that can shake up and down. So right, so the one on top won't budge, and the pulse almost tries to pull it, which by Newton's third law means gets pulled back down. And you can see at the bottom one then that the ring goes up, and then as it falls down, the ring creates the pulse going back. Here's another nice example from flipping physics. So rather than having a hard wall here, it's just somebody holding the end down, which does the job. Essentially, holding it down means it won't budge. So right, you see how, well, when the end doesn't budge, then it's like the pulse tries to pull it up as much as it can, but it won't work. So then it kind of gets pushed back down to the bottom, comes out flipped and moving to the left. Well, at the one on the bottom here without inversion, there's a free end, so it kind of moves up and then swings down, sending the pulse back to the left in the same shape. So what if we actually had like another type of rope or another type of string or even a slinky attached to the end, rather than having like a wall or a ring? You actually had some other material. They can actually send waves from one medium to the other, no problem. The situation changes though whether or not you're moving from a dense medium to a lighter one or the other way around. So as you send the wave through your string and you reach the middle of the two different mediums, the interface, then some of the pulse that you sent will actually get reflected back and some will keep moving through to the new medium. And obviously, if you look at the amplitudes of the two waves, then they're not ever going to be taller than the incident wave, the one you sent through, because they both carry some energy from your incident wave. So by conservation of energy, they can't be as the same as the one you sent. Now, in the case that you're sending a wave from a dense medium, so think like a heavy rope that's attached to maybe like a thin guitar string, then what you'll get is that at the interface, you'll get two pulses. One gets reflected back on the left and with the same orientation, just moving left, and then the transmitted pulse keeps moving to the right. And you see then in this GIF that the height of the two pulses is lower than the original. So in this case, if we think about the formula we talked about for wave speed on a string, we have that the linear mass density is bigger on the first medium than the second, and so we expect then that also the wave speed in the first medium is slower than on the second medium, and you can kind of see that how the wave travels a bit faster on the thinner medium. Then we can do this the other way around. We can pass it from a thin string to a thick rope, and when we do so, the reflected wave gets sent back upside down, gets sent back out of phase. And the reason that is because at the interface, when the wave kind of hits the point where the thicker string starts, it kind of has that same interaction where it kind of has the same interaction with, so there is a mistake here. It's not the free end reflection you're supposed to recall. It's more like the, I think I got them flipped, eh? Right. Okay, let me explain. Let me explain what I meant here. So here I'm saying that wave passing, that the way that a wave gets reflected as it moves from a light medium to a heavier one, it's kind of like what happens when a wave hits a wall where it tries to pull on the wall and kind of gets a counterforce that sent it back. In pulling it up, it gets a counterforce that pulls the wave down. So it's kind of what's happening here in the GIF, where like this wave in this like weak string tries to tug up on the thicker string on the right, and in doing so, kind of gets a counterforce that kind of overwhelms the original pulls and kind of sends some of it back down, reflected to the left, but some still gets transmitted through. And you can then think in the earlier example, when you have a heavier medium going into a lighter one, that it kind of behaves like the free end example I show you with the ring, where the heavy medium, the pulse, has an easy time just lifting up the interface and then bringing it back down to send the pulse back with the same orientation, just moving left. So, and again, one medium has a lower mass density than the other, so you move faster in a medium you move faster in a less dense medium. That's why the thin wire here, the pulse moves a lot faster than in the black wire, the thick black wire. And that's all for the recording. I hope you join me in the next one.